Hi, welcome to Unit 5 on sampling distributions in AP Statistics. This video is on topic 5.3, the central limit theorem. We are going to discuss a lot in this topic, and only at the end will I actually explain what the central limit theorem tells us. So all roads will lead to the big idea of this topic at the end. This topic covers such an importance of the title is actually not appropriate. I mean, the central limit theorem is huge, but I need this entire video to even get to the central limit theorem at the end. So please pay attention and be ready. There's not a whole lot of big problems that come out of this topic. It's really more a big idea that will lead to problems that we could solve in the future. So let's get right down to it. All right, three questions here. Why do we sample? Well, we sample because we want to know the true parameter of a population. That's why we sample. Whether it be that I want to know the true mean of a population or I want to know the true proportion of a population, I'm never going to get those truths until I take a sample. Okay, now that we found our sample statistic, is that true for the population parameter? When you take a sample, you're going to get a sample mean, you're going to get a sample proportion. But does that mean that our sample statistics are now true for the population? Absolutely not. Because it's just one sample, right? And samples vary. That's what we've been learning thus far. So just because our sample statistic revealed a value to us, it doesn't mean that that's what's true for the population. So this turns us right back to the very beginning. So how do I find the true population parameter? Well, it all starts by understanding what all possible sample statistics could look like. This is what this unit is all about. So even though we're only going to actually look at one sample statistic, one sample mean, or one sample proportion, we need to first understand what all possible sample statistics could look like. So how the heck do you do that? Well, start sampling. Sampling, sampling, sampling. So what is sampling? Well, looking at sample after sample after sample of the same size from the same population, right? When you put ing to the end of a verb, it means to keep doing it. If you tell me to jump, I'm going to jump one time. When you add ing on to jump, you get jumping, which means I'm just going to keep jumping over and over and over again. So when we talk about sampling, we're no longer talking about looking at one sample. We're talking about looking at sample after sample after sample after sample of the same size from the same population. The other key idea here is that we actually only take one sample, but we must think about what all those samples are going to look like. So for as many times in this video as you hear me talk about look at a sample, look at a sample, look at a sample, keep looking at samples, at the end of the day, you only ever really look at your sample, but you got to consider what all those other samples look like. All right. Moving forward, we have to recall what sampling variability is. This is why we sample, right? If it wasn't for sampling variability, there would be no reason to look at multiple samples. We'd only look at one sample, and that would be the answer. So remember, sampling variability is this idea that the value of a statistic will vary from sample to sample. If I look at the mean of a sample, and then I look at the mean of a second sample, and then I look at the mean of a third sample, and I look at the mean of a fourth sample, all of those sample means are going to be different. It doesn't mean I did anything wrong. It just is a natural occurrence that happens when you look at different samples. If we did not have this idea, then honestly, we wouldn't even need this class, because we would take a one sample and that one sample would be the same for all other samples, but that's not true. Understanding this idea is vital to everything we will learn in the future. Our job is to try to understand this natural variation better so that we can understand sampling. All right. So what would happen if we took a look at many samples? Again, sampling, right? Looking at sample after sample after sample. So let's just kind of walk through this, right? Well, first, we would have to take a large number of samples of the same size from the same population. If we don't actually do it, we could simulate doing it. Then we would find the sample statistic for each sample, either a mean or a proportion. You cannot do both at the same time. We are either going to focus on problems that deal with finding the mean of a sample, x bar, or we'll focus on problems finding the sample proportion from a sample, okay? So one at a time, okay? So regardless of what we're doing, we got to keep looking at that statistic. We got to keep finding the mean or the proportion of every single sample. then we can actually make a display of all of the sample statistics found. So imagine, we take a sample, we get an X bar, we get another X bar, we get another X bar. At the end of the day, we're going to have thousands of X bars in front of us, and what we need to do is make a display of all those X bars. That way we can learn from it. And remember, this is all the way back from Unit 1. When you look at a display, you have to talk about the shape of the display, you got to talk about the center of the display, and you got to talk about the spread. Now, if you're a little bit lost, like what the heck is he talking about? Let me clear it up with two examples, one for means and one for proportions. So the first one focuses on what is the mean amount of cereal in a box. So you got a box of cereal, and you want to know what the true mean is for all boxes, like the population mean. I want to know that. Well, I don't know, right? So what I'm going to do is I'm going to look at samples of size 50. So I'm going to look at 50 boxes. I'm going to find the mean of those 50 boxes. And then I'm going to do it again. 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 I'm going to continually do it as many times as I can. So again, make sure you process that. Get 50 boxes of cereal selected randomly. Let's just say Lucky Charms. I'm going to get 50 boxes of Lucky Charms selected randomly from all Lucky Charms boxes out there. I'm going to get a mean amount of cereal in those 50 boxes. I'm going to write that number down. Maybe it's 21.1 ounces. And then I'm going to do it again. I'm going to get another 50 boxes. And I'm going to get another mean. Maybe it's 19.8 ounces. And I'm just going to repeat that over and over and over again. And again, every time I collect a sample mean, I make a dot in my display. So if we look at this display here, we got a bunch of dots. And every dot represents the mean of 50 boxes. So essentially, we have a bunch of X bars. Every single one of these dots is an X bar, another X bar, another X bar, So for example, this dot right here, this dot was a box that weighed, let's see, 1, 2, 3, 4, 5, 6, about 21.6 ounces, somewhere in that neighborhood, right? And then you may notice that there were a lot of samples that were right around 19.8. There are several of them that were kind of stacking up there, right? That's kind of the center, right? We also notice a shape here. We see this nice and symmetric mound shape forming where there were very few samples with low averages. There were very few samples with high averages. Most boxes had an average somewhere 19.5 to 20.5. That's where most samples of 50 boxes came, right? So once you kind of put a dot on there for all your different samples, then you got to describe it, right? So that's what I did. I said, hey, this graph is symmetric, it's unimodal, it's got a center right around 19.8 ounces. If you actually take a mean of all the means. Now, that's a little bit tricky, so process what I said there. Every one of these dots represents the mean of 50 boxes. So if I were to take a mean of all the means, well, it was 19.89. So that's pretty accurate what the center of this graph looks like, right? And I could also calculate the standard deviation. The standard deviation is 0.56 ounces. And that actually makes some kind of sense, right? Because we know traditionally, if you look at the center, which is right around here, and you go up about 0.6 ounces, and you go up another 0.6 ounces, and you go up another 0.6 ounces. So if you go up 3 standard deviations, you should capture a lot of your data. And then if you go down 0.6, down 0.6, down 0.6, I'm being kind of approximate here, but you get the majority of your data, right? Okay. So the point is truly understanding what I did here. I didn't take a look at one sample. These dots don't represent one box of cereal. Each dot represents its own sample of 50 boxes. And each sample of 50 boxes has its own sample mean. So this is very different than anything we've ever looked at in the past. All right, let's look at another one here. This time, let's use proportion, right? What proportion of Skittles are red? I don't know. So let's take a sample of 20 Skittles. All right, we're gonna get all Skittles. There's millions of Skittles in this world. Look at 20 of them. Find out what proportion of that 20 are red. Put a dot for that spot, right? And then repeat it and repeat it and repeat it, right? That's sampling. So take 20 Skittles, find the proportion of red. Take another 20, find the proportion of the red. Take another 20, find the proportion of red. So this time, each dot represents a sample of 20. For example, this dot right here represents a sample of 20 Skittles, and in that particular sample, 32% were red. Here's another dot right here. This dot also represents 20 Skittles, and in that sample, 28% were red. So again, every dot doesn't represent one Skittle. Every dot represents a sample of 20 Skittles and what that sample was. So essentially, this is a bunch of p-hats. Every single one of these dots is its own p-hat, its own sample proportion. And what I can see here is I see a nice shape, right? I see a nice symmetric mound shape where very few samples were extremely low percentage of red. Very few samples were extremely high percentage of red. Most were kind of in the middle, right around 30%. So what do you know? I would say the center is about 30%, 0.3, right? Now, if you actually take a mean of all these p-hats, now remember, every one of these dots is a number. Every one of these dots is its own p-hat. If I were to take the mean of all of these proportions, I would get 0.296. I actually did that, right? I actually took the time to do that. I didn't want you to do it, waste time. But again, pretty darn close to 30%. But again, there was some variation, right? Some samples were a little higher, some samples were a little bit lower. So the standard deviation was 0.034, right around 3%. So once again, if I were to go up 3%, go up another 3%, go up another 3%, I'm hovering right around that 3 standard deviations that captures the large majority of my data. Same thing if I were to go down 3%, go down 3%, go down 3%. Again, I do capture the large majority of data. All right? And then actually, it's not exactly 3%. It's about 3.4%. But you get the idea. So the most important thing I need you to understand here is that this is what happens when you sample, right? You get a distribution that looks very familiar to us. I mean, we have seen displays like this before in terms of what it looks like. But what this display represents is very different than anything we've seen before. So this one was cereals. Every single one of these dots was its own X bars. I got a bunch of X bars, a bunch of sample means. Down in this case, I got a bunch of p-hats, a bunch of sample proportions. And this is what happens when you sampling, right? When you repeatedly sample. All right, now this is what's called a sampling distribution, right? And this is what this entire unit is about. So the last two distributions were the start of a sampling distribution, which show all possible sample statistics, right? Now, the reason why these last two examples were not official sampling distributions is because they didn't show all possible samples. The idea of a true sampling distribution of a statistic is the distribution of values for the statistics for all possible samples of a given size from a given population, all right? So if you're thinking about, when I write the word here, all possible values of a statistic, remember there's two statistics that we really look at. We look at sample proportions and sample means. So imagine you looked at every possible sample out there and you found the p-hat for every possible sample and you made a display of it. That's a sampling distribution. Same thing for means. Imagine you were to look at every possible sample and you found the X bar, the sample mean of every sample, and you were to look at a picture of it. That's a sampling distribution. Now, we focus in this class on proportions and means, but you can even do it for medians, right? You could find the median of every possible sample, and boom, that's a sampling distribution for the median. You can even do it for range. I mean, most people, this isn't very common, especially in this class, but you could do it. You could find the range of your sample, max minus min, and find the range of another sample, of another sample, of another sample, and take all of those ranges and make a display of it. That's a sampling distribution. So what is a sampling distribution? I'm going to ask you this question 1,000 times. You better know the answer every single time, right? It's a distribution of all possible sample statistics of a given size from a given population. Well, now, this is the first time you're ever learning this, so you might not totally understand it, but let's try to explain it one more time. Let's go back to cereal boxes, right? How many boxes of Lucky Charms are out there? I mean, there's got to be millions, right? I mean, millions of boxes of Lucky Charms. And if you're going to look at a sample of 50, how many samples of 50 do you think are out there? Now, I mean different samples, right? So if I have 50 boxes of Lucky Charms and I just switch one box with a different box that wasn't originally picked, boom, I got myself a different sample. Well, I mean, if you actually go back to what we learned in the last unit, you could actually go to your calculator. You could do 1 million, choose 50. And that'll tell you how many different samples of 50 you could pick from a million. And I'm going to tell you right now, your calculator is going to say overflow because it's that many. I mean, there are thousands, hundreds of thousands of samples of size 50 that could be pulled from millions. In fact, it's probably even more than that. So the point is that sampling distributions, to fully create a sampling distribution, it's technically impossible, to be honest, because you're never going to actually be able to look at every possible sample. Even if you do an example of like people, right? You know, what's the average weight of a person? And you looked at a sample of 50 people. If you just replace Sally with Carl, you got yourself a whole new sample, right? So that's why there are so many different samples out there. But a true sampling distribution will show you the mean of every single possible sample or the proportion of every single possible sample. Or, like I mentioned, you could even do the median, but it's got to be of every single possible sample of the same size. You can't switch your sample size from the same population. You can't start picking from a different group, right? So the point I'm trying to get you to understand here is that sampling distributions are super important. But what they actually are they're kind of more theoretical. You just have to understand that they do exist, but actually finding and creating a sampling distribution could be very, very painstaking because you got to find every possible sample. All right, so statistics from all possible samples, right? Let's say this yet again based on our two examples, right? Imagine if we were to look at every possible sample of 20 marbles from a bag, and then look at the proportion of red marbles in each sample. Then we made a dot plot of every single sample proportion. This would be a sampling distribution, right? So, let's try to put on a small scale. Like, let's say we had a bag, and that bag only had 200 marbles in it, right? As opposed to the billions of Skittles that are probably out there, right? So you got 200 marbles in the bag, and think about how many different samples of 20 there are, right? I can actually use my calculator for this and do 200, choose 20. And believe it or not, you're going to be mind blown by this. But how many different samples of size 20 could be taken from a bag of 200 is 1.6 times 10 to the 27. It's an enormous number, right? And even that's a small scale example. It's huge, right? But the idea is that if I were to find the proportion of red marbles from every one of those samples, and I were to make a dot plot of all those p hats, that is a sampling distribution. It's a picture of all possible sample proportions. Or again, imagine if I were to look at all possible sample means of 50 boxes of cereal, right? Again, my example that I had up here is a nice picture, but I mean, come on, I can count those dots. There's not that many dots in this graph. A true sampling distribution would have a dot for every possible sample mean that's out there from that population of the same size. That's a true sampling distribution. All right, so let's try to practice this, right? What is the sampling distribution for the mean weight of samples of 30 rabbits selected from all rabbits in Pennsylvania? I mean, there's got to be thousands of rabbits in Pennsylvania, probably millions, right? Okay, so what would be the sampling distribution? Well, it would be looking at all possible samples of 30 rabbits, and it would be looking at the mean of every single one of those samples. And then it would be a distribution showing me all the possible sample means for all possible samples of 30 rabbits, right? So I'm imagining, a big dot plot and a bunch of dots, and every time I get a sample, I get a sample mean. And for every sample of 30 rabbits, I find the mean. And sometimes I might get a group of really fat rabbits, and I got a big mean. I might get a group of small rabbits, I get a small mean. But over the course of the billions and thousands of samples out there, most samples are going to start to pile up around the center. And I'm going to get this distribution here, and I'm going to be able to get a shape of it. You could see it's symmetric, mound shaped. I'm going to be able to get a center. Hey, typically the sample came back with a mean of 12.2 ounces, right? And I'm also going to get a spread. The spread is the fact that some samples are going to be higher, some samples are going to be lower. So, whoa boy, you know, the whole unit is called sampling distributions. By now, if you need to pause and go back, please do so. I hope by now you understand what a sampling distribution is. But now what I want you to know is what it's not. A sampling distribution is not the distribution of a single sample. It's not the distribution of the entire population. It's a distribution of all possible values of a statistic from all possible samples of the same size from the same population. So, you know, let's try to break this down. Imagine if I were to look at one sample of 30 rabbits. Every dot would represent a single rabbit in that sample. And I would probably have some bigger rabbits, some smaller rabbits, yada, 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 right? Imagine if I were to look at all rabbits in Pennsylvania. I don't know, maybe there's 1.3 million rabbits. I don't know, I'm just spitballing. And, you know, now first off, it's going to be impossible to find all those rabbits, but maybe I could use some type of model, like a curve, to represent those rabbits. But again, I'm looking at all of them. Versus what I'm doing now, what we're doing in this unit is we're looking at sampling distributions. Sampling distributions is a way that we represent all possible sample means or proportions, right? One at a time. Don't do them both together. Where again, now I'm thinking about a dot plot where each dot does not represent one rabbit. Each dot represents a sample of rabbits and what the mean of that sample was. That's a sampling distribution. Here's kind of a nicer look at this, a little bit more organized. So imagine we were to look at, you know, a group of rabbits, right? Now again, you know, my numbers are not necessarily true, but let's look at one sample of n individuals, right? One sample. Here is a dot plot. Every dot represents one sample. Maybe this is some type of reading test. And if you look at this, most people are around 5. They score 5 on the reading test. But there were a couple really smart people that scored higher, a couple, you know, slightly less smart people that scored lower. But the point is this is just one sample. Every dot represents one person. Now, then I could kind of theoretically envision, well, you know, what would all individuals look like, right? You know, let's just say we're talking about all third graders in Ohio. Well, there's, you know, hundreds of thousands of third graders in Ohio. So maybe I'd use a curve to represent that. And that curve could be a theoretical view of what all those third grader reading scores could be. You know, most kids are probably going to get around a 5. Some kids could do better. Some kids could do lower. You get the point. But what's a sampling distribution? That's what this unit's all about. That's a distribution of all possible values of a statistic from all possible samples of the same size. So now, if we're going to take a look at a sampling distribution, when I put a dot right here, that dot no longer represents a single person. That dot represents a group of n and what the mean was for that group. Here's another dot, another group of n, what their mean was. And every single dot represents the mean of a sample. I hope, you know, you might be getting bored with this, but I know as many times as I can explain this to you, the more you'll get it, okay? All right, so how do you create a sampling distribution? Because if you've been listening to me, I'm telling you it's pretty much impossible. Well, it does require a lot of work because you would literally need to know all possible samples of size n taken from the population. And honestly, it's pretty impossible to do. But what we can do is we can use computers to simulate taking a lot of samples for us. Because computers could do things pretty quick. So we could have a computer simulate a sample, get a statistic. Simulate a sample, get a statistic. And it could do so, and then it can make a graph for us pretty quick, right? But understand, in truth, a sampling distribution is more of a theoretical idea that you need to understand. These distributions do exist, but it's really difficult to truly create one. All right, so here's another example. Kyle sets out to find the mean length of bluegill fish in Lake Erie. So he selected a sample of 35 bluegills from Lake Erie, and his sample was 7.9 inches. So he got one sample, and his mean was 7.9. Okay, he then used a computer simulation package to create a sampling distribution. to show the sample mean of 200 samples of 35 bluegill fish. So every dot represents a sample of 35 bluegill fish. Now, he did this 200 times. Now, is that a sampling distribution? Honestly, no. But it's a pretty good start. But remember, a true sampling distribution would show all possible sample means from all possible samples. I'm going to tell you right now, there's a lot of bluegill fish in Lake Erie, so there's a lot more than 200 samples, but this is a pretty good start. So every dot represents a sample, and now he can kind of get a feel for this, right? He sees, wow, there are a lot of samples, a lot of samples are around 13.5 inches. That kind of seems to be the center, right around 13.5. And there were some higher samples that came back, 18, 19 inches on average. And there were some lower samples. What could cause a really high sample? Well, if you get one really big bluegill fish in your sample, then it's going to throw off that one sample to look higher. Or same thing down here, right? What could cause a really low sample? Maybe you get one teeny tiny bluegill fish, little baby fish, and that causes your whole sample to, on average, be smaller. But, those samples were very few and far between. Not a whole lot of those samples. Most samples were right around 13, 14 inches on average, okay? So each dot is the mean of a sample. Now, again, this is not a true sampling distribution, but it's a really good start. Because remember, a true sampling distribution shows all possible samples. All right, now I'm finally ready to talk to you about the central limit theorem. The central limit theorem, which a lot of people just abbreviate CLT, states that when a sample size is sufficiently large, a sampling distribution of the mean of a random sample will be approximately normally distributed. Now, you might be like, okay, a lot of build-up to this? Guys, I can't tell you how powerful this is. Essentially, what the central limit theorem says is that as long as your sample size is pretty big, your sampling distribution will always follow a normal distribution. That's awesome because we just got done learning about how easy the normal model is to work with. So if we understand that we don't have to actually find a sampling distribution because, again, there's too many samples out there. But if we know ahead of time that it's going to be normal, oh my gosh, it's going to help us tremendously. Now, the central limit theorem does require that all samples must be selected randomly. Well, come on, we did a whole unit on that you have to do it randomly or else it's going to be biased. It does require that sample size be sufficiently large. Now, every stats teacher's definition of what sufficiently large is a little different, but in our class, it's got to be greater than or equal to 30. A good sample size needs to be 30 or larger when it comes to working with means. Some people might say it's got to be 50. Others might even go a little lower, but for our class, we're going to say a pretty big sample needs to be 30 or more. All right. And the central limit theorem does require that the sample values are independent of each other, which means that each sample is independent of the next, which technically means when we pull out those 35 bluegill fish and we measure their average, we have to put them all back, mix up the water, and pick out a brand new set of 35. That's what will allow us to truly have independence between samples. All right. Now, once again, this theorem is so powerful. Here's why. Let's just say that we have a population that's skewed right. And that might be true for our bluegill fish. I'm sorry, skewed left. Where, most bluegill fish weigh something up here and there's very few super small bluegill fish, right? That's a skewed left representation. And imagine if we were to take out single samples, like if we were to take out a sample of 35, well, if its population skewed left, well then one sample is probably going to be skewed left too. Here's another sample of 35. Here's another sample of 35. Here's another sample of 35. Again, if your population is skewed left, guess what? Your individual samples will probably be skewed left as well. But here's where the central limit theorem kicks in. The sampling distribution is always going to be normal, even if your population is skewed. So what we're trying to say here is when you make a graph of the mean of each of those samples, right? Even though each of those samples are skewed, when you start making a graph where each dot represents the mean of a sample, that distribution, the sampling distribution, will always be normal. That's what the central limit theorem tells us. super powerful because we love the normal model. It always works out this way. It's really powerful. I'm going to talk a lot more about it. And I know that you might not really care about how powerful it is because in your world it doesn't really matter. But I'm telling you, in the world of statistics, this is big. Now, the central limit theorem is only true for means. But what about proportions? Well, actually, don't worry about it. If, we don't even need the central limit theorem for proportions. It's actually kind of known. I mean, for a sampling distribution for the proportion, it will always be normal. Honestly, we'll talk more about that later in on upcoming videos. But anytime you're looking at a bunch of p-hats, which is a sampling distribution, looking at a ton of p-hats, and you put them all together where every single dot represents the p-hat of a sample, that will always be normal. And that's just what we saw back in the very, very beginning. I mean, look at these examples way back here. Hey, kind of look normal. Hey, kind of look normal. And that is true. Now, for means, the central limit theorem tells us it's always going to be normal. For proportions, it just always is going to be normal no matter what. All right, so let's look at one final example here. This time we're going to deal with proportions. I just want to make sure you understand that it works with proportions just like it works with means. All right, Ray set out to determine what proportion of students at her large high school did their homework last night. Okay, so she sampled 40 kids and 61% did their homework. But she wanted to think about what all other possible samples could look like. I mean, she only did one sample. There's thousands of other samples out there of 40 students. So she had a computer simulation package create a sampling distribution to show the sample proportion of 200 samples of 40 students. So every single one of these dots represents a p-hat. For example, right here is a p-hat. Right around about 54% of kids in that sample did their homework. Here's a sample right here, which is right about, I don't know, maybe 72% of kids in that sample did their homework. But again, every single one of these dots represents a p-hat. Now, look at the shape. It's normal. Very few samples came back low. Very few samples came back super high. Most samples came back right around 67%, somewhere right around there. So remember, please remember, this is not a true sampling distribution because we only looked at 200 samples. A true sampling distribution looks at all possible samples. But I'm going to be honest with you. True sampling distributions are a little bit more theoretical because you won't see them happen too often because they're really hard to actually find all possible samples. But the most important thing is that you understand that it's going to be normal, whether you're working with means, here's the means of a bunch of samples of fish, or the proportions of a bunch of samples of students. They're always going to be normal. And that's where the central limit theorem helps us. So why do we need sampling distributions, right? Again, this is really super important for everything we do the rest of the class, but this might make a little bit of sense right now. Sampling distributions are very powerful because they show us what all possible sample values of a sample statistics could be from a sample size n taken from the same population. I've probably said this sentence 8 times. This is the definition of a sampling distribution, which is why they're so important. Now, why do we need them? Because they allow us to see if our sample is significant or not. Let's go back to this example looking at the proportion of kids that do their homework. Notice that Ray's sample came back at 61%. Is her sample significant? Well, 61% is somewhere right around here. And there were plenty of samples that were even lower than her sample. So I'm going to go ahead and say no. Her sample was actually pretty close to the center. It wasn't that far away. So I don't think her sample was extremely low or significantly low. I think that she had a little bit of a lower sample simply because of sampling variability. Not every sample is going to come back what is true. Now let's go back to our fish. Kyle had a mean of 7.9. Is his sample significant? I'm going to go ahead and say yes. It looks about only 2 samples came back that low. 2 out of 200. Now, 2 out of 200 is about 1%. There's my significant number. Only 1% of samples were as low as Kyle's. So I'm going to go ahead and say that Kyle's sample was pretty low. I mean, look at how many samples were 12, 13, 14, 15 inches on average. 7.9 was unlikely. So remember, when something significant happens, we need to find out why. So I'm going to be like, Kyle, dude, like, did you lie to me? Or did you go to a certain spot of Lake Erie where there were only tiny bluegill? I mean, what happened, Kyle? Because a sample as small as yours is very unlikely. But when we go down to our friend Ray, her sample wasn't really that low. It really wasn't that unlikely. I wouldn't second guess her sample at all. I wouldn't tell her that her sample was weird. I wouldn't be like, Ray, what happened to your sample? I'd be like, Ray, you just had a very, here's the word, normal sample. Whereas Kyle had a really significant sample. So that understanding, what I just finished explaining, is really why we need sampling distributions. Because what we want to know is our sample special? And the only way to answer that is to think about all possible samples. And that's what a sampling distribution will do for us. All right, guys, I know that was a lot. I know there's a lot of theory and theoretical and concepts in this video, but it's really important you understand this idea of the central limit theorem and how it helps us truly understand sampling distributions.